Welcome back to part 2 of ionic compounds. Again, most of what you'll name. They are formed between a metal, which is most of the periodic table, or ammonium, which is a polyatomic ion. We'll talk about in a second. But again, your book doesn't always say the ammonium ion, and yet they love to put it on exams. So if you see a metal or the ammonium ion, and they're always written first, then you have an ionic compound. And then it bonds with the thing that's written second, which is the nonmetal compound. The metals lose electrons to become a positive ion. We call those cations. Nonmetals tend to gain electrons to become a negative ion, anions. In nature, many metals are naturally in their positive ion state because they're more stable like this. Nonmetals in nature are in the negative ion state, the anion state, because it's more stable. But when you look at a periodic table, unless they tell you it's charged, you assume that it has no charge. So ionic compounds, again, are positive and negative ions, which are balanced out. So you won't have a net negative or a net positive. We can do this with substances. We can do it temporarily, but naturally, you always have positive balancing out negative, so your net compound is neutral. So it's formed between a metal, again, or ammonium, and a nonmetal. The positive and the negative ions are attracted to each other in a ratio so that the resulting compound is neutral. That means you have to have the same number of positive as you do negative ions in your compound. A really simple example that you see on a daily level would be sodium plus. It comes from group 1 on the periodic table, the alkali metals. And so it tends to form a positive 1 charge, but they just write positive. And chloride. Notice that chlorine is now called chloride because things with a negative charge on the periodic table end in an IDE as soon as they have their negative charge. So it is sodium plus and it is chloride minus, but in the formula we write it as NaCl because the two charges, when you put them together, balance out. So in the final form you write NaCl. Does this mean it no longer has charge existing on the sodium and the chloride? No, the charge still exists. We just don't draw it in the final form because we have balanced out the charge so that the net charge is 0. But as soon as sodium chloride hits water, it would separate into the sodium ions and the chloride ions like we saw on the first slide in part 1. So now we're going to look at naming ionic compounds. Cation first, so positive ion first, and then your anion, which means metal first, or in rare cases the ammonium, the NH4+, and then the nonmetal comes second. They will say monoatomic cation when they mean that it comes from the periodic table. It doesn't mean that there's just one. When you do the final compound, there can be more than one, but monoatomic means it's coming from the periodic table. There's only one type of ion there. So K plus is from group 1, just like sodium. And so it's an alkali metal, and we call it potassium ion. A monoatomic anion, again, comes from the periodic table, meaning it's not bonded to anything else. We'll talk about these in a second. As soon as you have an anion from the periodic table, it goes from chlorine, which in nature is Cl2, to chloride, which means it now has an IDE ending, to tell us that it now has a negative charge. It's an anion. So potassium chloride, we'd put the K plus and the Cl minus together. The plus and the minus would total 0, so the net charge is 0. And what is it used for? It can be used for many things, but one of the things it can be used for is to stop the heart. And they will also, we'll come back to it later, it's also used in medicine as a potassium supplement. So one of the things that is nice to look at when you are learning naming is a periodic table that has the charges written on them. And notice that group 1A are your alkali metals. Hydrogen's kind of hanging out here, it's not a metal. You have lithium, sodium, potassium, rubidium, cesium, and francium. And they all have a positive 1 charge. Then you have group 2A, alkaline earth metals, and these are called alkaline earth metals because both the alkali and the alkaline tend to form bases in water or when they react. They're very reactive, and group 2A forms +2 beryllium, +2 magnesium. You get calcium +2, strontium +2, barium +2, radium +2. Then you get to the transition region, and these are labeled the B groups. The A groups are often called the main group elements, and they're here and here. And then the transition metals can have various charges. They call these different oxidation states. When you hear that term oxidation state, that just means charge. It's another fancy word like nomenclature for charge. So when they say, what is the oxidation state on sodium, they mean what is the common charge on sodium? And you would say plus because it's in group 1. Here, for the transition metals, they've listed the 2 most common charges for many of the transition metals, but many transition metals, like chromium, have many different possible charges. You don't have to memorize these. Students always worry that they have to memorize all the possible charges for the transition metals. No, you do not have to memorize these. And then notice that when you get to group 3, plus 3 for aluminum. When you get to group 4, the metals tend to be plus 4, but you have some transition metals in here as well. Tin and lead can transition. They're 2 most common, plus 2 and plus 4. When you get to group 5, you have more of the nonmetals. And again, nonmetals tend to form negative charge. They tend to gain electrons. So we have minus 3 for group 5A, minus 2 for group 6A, minus 1 for the halogens, fluorine, chlorine, bromine, iodine. But it's important to know that the halogens, when they don't have a charge, they would be F2, Cl2, Br2, I2. They are diatomics in nature, so they naturally have twins. The chemistry name is a diatomic. Hydrogen's the same way. It's naturally H2 in nature. O2 when it doesn't have a charge, and N2 when it doesn't have a charge. And then the noble gases right here tend to not form any charges. So we'll just say 0. These will be called now fluoride, chloride, bromide, iodide, oxide, sulfide, selenide, nitride, phosphide. Because again, monoatomic ions, so ions that are on the periodic table, as soon as they get their negative charge, they end in IDE. Whereas the positively charged ions, like lithium, would just be lithium ion. Or they could say lithium cation, sodium ion, or sodium cation. So let's look at some nomenclature, simple ionic compounds. You name the positive, and it's just named like it would be on the periodic table. And then you change the ending to IDE if it's with a nonmetal from the periodic table. So sodium chloride, it's an IV fluid. IV fluid is 0.9% sodium chloride. It's also table salt. Zinc oxide is a common astringent in healthcare. Potassium chloride is a common potassium supplement used for hypokalemia, but again, it's also one of the 3 things used to stop the heart. Let's practice. So try naming, take a second and try naming this compound right here. This would be called the Ionic formula. And it is typically used on ice. It's very good at melting ice. And if you named it correctly, you would name this calcium and you would name this chloride. It doesn't matter that there's a 2 here. You don't say how many with an ionic compound. You just say calcium chloride. Take a moment and try and name the second one. And it's commonly added to toothpaste, and you would have named it sodium fluoride. Again, you don't use numbers to tell how many, not with ionic compounds. So most of the time, you'll just be saying calcium chloride, sodium fluoride. You don't say how many based on the numbers. And notice that in ionic compounds, we don't write the number 1.